Okay, so I'm honored to be the first talk after the keynote. Today I'm going to talk about new features in our HSDS, which is the HDF server. I've talked in previous EU Hugs, and if you're not familiar at all with HSDS, it might be useful to review some of those previous talks. And this talk, I just want to talk about new stuff. But I will give a brief overview of HSDS, some different ways you can deploy the server. And then new features, we have our streaming support, and then fancy indexing. And finally, I'll give a few case studies. Some people actually using HSDS. So, oftentimes we think of HDF5 as amalgamation of, there's this library of a C API, there's a file format, and a data model. And it can be a challenge trying to use exactly that in a cloud context. What we do with HSDS is kind of loosen the file format aspect, and as a result, have a system that's much more applicable to cloud deployments. So the idea is we want to have a REST-based API rather than a C library API. Secondly, to utilize object storage because that's most prevalent in the cloud. You can use POSIX storage as well, but it's primarily designed for use of object storage. And thirdly, we want to support elastic compute, by which means we can scale up or down the amount of resources we're utilizing for the server. And we want compatibility, so it works with your existing HDF applications. And so how this works is that, HDF5 files store data sets and groups and attributes all within one file. In HSDS, we have a cloud schema, and it works by storing each data set or group or link as a JSON object, and each chunk as a binary object. So if you imagine this grid as a data set, and these heavy lines are the chunks. Okay, chunks are kind of like the internal subdivision of HDF5 data sets. Each of those chunks will be stored as a separate object within the object storage system. And then we want to do a selection on this data set, say a yellow rectangle. It's going to be crossing some number of these chunks. And for each of these pieces where it intersects a chunk, we need to segment out that piece and finally glue it all back together and send that request back to the user. And in this kind of high-level architecture, we have on the right an object store. So recall that each chunk is stored as a separate object. And within this object store, there's this virtual partitioning. And the number of partitions will be based on the number of container nodes, these data nodes we have in the middle. So each data node owns exactly one partition. So each object is read or written by exactly one data node. And what this means is that a data node becomes the authority of reference for a given object. So a data node can do things like cache the data, so that's read back from the storage each time. It can manage like multiple updates to a given chunk, and so on. On the left, we have a client. A client would typically go through a load balancer, and the load balancer would wind up on these service nodes. The service nodes are the containers that process requests, authenticate user, authorize the action, and then figure out which of these data nodes are needed to perform the actual request. So if I'm writing to, say, a given chunk or a set of chunks, there'll be one or more data nodes that are needed for that request. So overall, the features. Is there a question? Hello? Can anyone hear me?
We can certainly hear you. I think it was just random background noise.
Oh, okay, okay. I go on. So it's the API that lets you read and write just the need. We support compression. In fact, we support most of the features of HDF library. And it's scalable in that requests get parallelized across multiple nodes, which means that, it's not like HSDS parallel or not. Each request can be parallelized across the set of data nodes we have set up on the server, meaning the more data nodes, the faster your performance is, not only for more clients, but also individual requests get parallelized across those data nodes. Unlike with HDF5, it supports multiple writer, multiple reader, meaning that you have multiple clients, and these clients can be reading and writing to the same objects at the same time. So from the client side, so the pink box is the HDF server. On the client side, we could have C and Fortran applications talking to the H5 library through the RESTful plugin. We also could have Python applications, which would normally use H5Py, can use H5PyD. And H5PyD emulates H5Py in terms of its API, but rather than talking to a library, it makes REST requests that go off to the server. And there are command line tools based upon H5PyD for things like uploading files to the server, listing content, updating ACLs, and so on. And then finally, you can have web applications. So here I put in the H5 Web React components that ESRF is working on. But you can have web applications that directly use either these components or directly use the REST API to have maybe visualizations directly from the browser. A little more about H5PyD. It's a pure Python package. It supports most of the H5Py API. Also, it has some extensions for things like listing constant folders, updating ACLs. It has a PyTable-like query interface. And beyond that, the packages H5, NetCDF, and X-Ray can use either H5Py or H5PyD depending upon the file format you have. So if you have the HTTP / prefix, it'll use H5PyD, otherwise we'll use H5Py. Okay, now let's talk about different ways to deploy HSDS, and the number of deployments has multiplied over the years. So first of all, we have Docker. Secondly, Kubernetes. Thirdly, AWS Lambda. And lastly, H5PyD Direct. And these all have pros and cons, and I'll talk a little bit about each of these in turn. So originally, we just had HSDS and Docker. And this works by having either an EC2 instance or just a workstation running Docker. And the SN and DN are HSDS containers that run on Docker. The DNs talk to a storage system, maybe S3, and you can have clients running on this E2 instance that are talking to localhost to SN, and the SN container would make requests to DN containers, and the DN containers would make requests to the storage system. Also, you can have external clients that are going through a DNS hostname and a port to get to the SN. So this is all well and good. A few provisos. The number of data nodes is fixed at startup, so you can't dynamically change it. Obviously, you can't add more machines, right? So if your capacity is beyond the limit of one machine, you're pretty much stuck with that. There's only one SN container. So if the SN happens to be the bottleneck, which could be true in some applications, that'll limit your performance. And lastly, it's a little hard in Docker to have other containers talk to co-containers on Docker. Just remember that. So next we have Kubernetes. Kubernetes has a concept of pods. So pods are the minimal deployable unit in Kubernetes. And we configured HSDS on Kubernetes such that each pod has a SN and a DN container. So when you deploy an HSDS pod, you get one SN and one DN. The thing about Kubernetes is that you can deploy as many pods as you have capacity for in your cluster. So if I want to deploy, 4 HSDS pods, it's fine. I can then change that, say, deploy 16 or 32. As long as I have capacity in terms of memory and CPU, I can deploy more pods. Now, if you need even more capacity, you can add more hosts to your cluster. So the thing about HSDS pods is that each pod talks to its sibling pods. So again, we have a request going to the SN container. It will talk not only to its own DN, but to other DNs in other pods. So again, by having more pods, you get not only more capacity, but you get more parallelization going on. One nice thing about Kubernetes is that you can have application pods running on the same cluster, talking to HSDS pods through an internal service point. And naturally, you can have external clients going through a Kubernetes ingress controller talking to the HSDS pods as well. You usually get a little better performance by having a native Kubernetes application talking to HSDS pods. Okay, so is this a kind of a classic producer-consumer problem? If you add a lot of job pods, that puts more load on HSDS, and now your challenge will be you need to scale up the number of HSDS pods to match that load. It's not hard, but it's something you need to be aware of. There's an alternative way of deploying HSDS Kubernetes where we have an application, and in that application, we bundle a service node and one or more data nodes within one pod. So now your application is talking on localhost to the service node. The service node is talking on localhost to the data nodes. And the nice thing about this approach is that when you scale up your application, by running my application from one pod, now I want to run on 10 pods, the HSDS components naturally scale up with that. So if I have 10 application pods, I'll have 10 SN containers in those pods, and I'll have 40, say, DN containers. The downside of this is that there's no coordination between multiple pods. For example, say I have pod 1 writing to even number of rows of a data set, and pod 2 writing to odd number of rows of a data set, they would overwrite each other's updates. So don't do that. Next, we have Lambda. So Lambda is AWS's approach of serverless computing. With Lambda, you don't provision a server and precode on it. You just tell Amazon, hey, Amazon, I want to run this function. And Amazon will bill you for the number of seconds that it takes to execute your function. So this is very nice because you have this elasticity in the number of Lambda functions you have running. So by default, you can have up to 1,000 simultaneous Lambda invocations. So we can have H5PyD talk directly to a HSDS Lambda function, talking to storage. Or if you have a REST client, it can go through the Amazon API gateway. The API gateway can provide a REST-based facade to a Lambda function. So it looks like a normal web service from here, but it's actually being invoked as Lambda functions. The bad thing with Lambda is that there's a startup cost per each invocation. It takes up to 2 seconds for the Lambda function to spin up. The more you run, the faster it goes, but it's always much slower than, say, executing a function on a server. There's also limitations on the size of the request and response you can send. And there's a limit how long it can take to run a request. And finally, it doesn't support binary request responses. Everything has to be JSON, which has a little more overhead for requests that are trying to marshal a lot of data. And then finally, we have H5PyD Direct. H5PyD Direct is another way to run serverless, but here we have H5PyD invoking subprocesses on a machine where the application is running. So when you do a file open, H5PyD will create these SN and DN not as containers, but as subprocesses, and they communicate using Unix sockets. So file open, you'll start these processes, and then there's no per call overhead, and as soon as you file close, the subprocesses go away. So this is nice in that, again, there's no server to set up, right? It just works like a normal H5Py application, except that there's under the covers subprocess and parallelization happening. So here's an interesting chart that kind of shows the advantages of Lambda. Here you see these, basically it's time on the x-axis and how long it took to instantiate some number of containers from 0 to 3,000. With Kubernetes, so EKS is basically Kubernetes on EC2. With Kubernetes, it takes at least 2 minutes to create your first container. That's just the startup time on the server and so on. And then it kind of ramps up linearly up to 3,000. So 5 minutes doesn't seem long, but if you are having to dynamically respond to, say, user input, that's a long time to ask someone to wait. Conversely, with Lambda, you can hardly see it here, but it's basically the vertical line along the left border. So you can go from 0 to 3,000 implications almost immediately. So that's kind of this benefit, right? If you have loads which are highly dynamic, you can create these Lambda functions as needed, and you're not spending money, say, managing a server running 24/7, which is only used sporadically. Next, I want to talk about some other new features, one of which is streaming support. So since it was started, HSDS has a limit on how many chunks could be accessed per request and how many megabytes could be read or written per request. And the reason of this was that when HSDS was processing a request, it had to allocate memory to store the response or the input data. And then that memory would live for the lifetime of that request. And if the request, say, was to write a gigabyte of data, and the server tried to allocate a gigabyte, it wouldn't have enough memory. So that's kind of annoying for some clients. They'd be forced to paginate on their side. So rather than 1 gigabyte request, they would say maybe do 10 100 megabyte requests. But now we have this internal pagination in HSDS. So no matter how large a request is, HSDS can process it kind of gradually without committing overly large amount of memory. And on the client side, you'll start seeing bytes come back from your request even before the server is finished processing all the chunks of the request. So your client could conceivably be doing useful work as bytes start streaming out of the server while the server is still processing remaining chunks in the request. Another feature we have is fancy indexing. So in fancy indexing, rather than a point selection or hypertext selection, you have a selection where you have maybe either a start plus stop plus stride on one dimension and a set of indexes on another, or in a combination. For example, if I have a data set and I want, in the first dimension, this range 0 to 100, And the second dimension, I want indices 1, 4, 63, 92. Right? So that's not a point selection, it's not a hypertype selection, but it's a very common operation in a lot of fields. So previously, you had to do this by sending one request at a time for each of those columns. And now you can send one request that gets all the data for all the columns. And because of how how we can pull these columns in the same time, you can see quite dramatic speed up to 8 times the performance of doing this row by row request. And also we see good scaling as the number of nodes in the server increases. So here I had a test case where I'm taking 4,000 columns from a 17,000 by 2 million size data set with 4 HSDS nodes. That took 65 seconds. If I go up to 8 nodes, it's 35 seconds, and 16 nodes is 23 seconds. So again, it's one request retrieving 4,000 columns from this rather large data set. And every time I increase the size of HSDS, I get almost a doubling of the performance. Finally, I just want to mention HDF or HDF Lab. This is a free Jupyter Lab environment we provide on the HDF group. And if you want to try out HSDS, but don't want to go through the bother of doing any kind of setup, you can go to this Key Lab and get an environment that basically gives you a kind of a mini server with a 10 gigabyte of local storage that has access to HSDS instance. Okay, finally, a few case studies. We've worked with NREL, the National Renewable Energy Laboratory, for a few years now, and they've have petabytes of environmental data that is accessible to the public, and a large percentage of this uses HSDS. By using HSDS, they enable users to get just a slice, just maybe a time range or region selection of the data they want, rather than having to download all the data, which is many terabytes. And they've recently started to use Lambda functions because, again, they have a use case where the load is highly variable because they don't control when external users will be accessing the server. So it can go from very little to very much in a short time. And so using Lambda, they can kind of scale up to meet that demand. So their infrastructure, they have 6 physical servers managing their data download API. And that's talking to 3 EC2 clusters, 4 to 12 instances each with 8 cores. So quite a fair bit of hardware they have. And on top of that, they are using HSDS Lambda for spike loads. Another use case is Biosimulations. So Biosimulations is running HSDS with Kubernetes. They have a very nice blog article we have on our website. And I would also invite you to attend Jonathan's presentation tomorrow, where he'll talk in detail about the use case. And then finally, we have UVA Art. This is a NSF project that is collecting environmental data from a sensor network. So they have these sensors in the field that collect information like temperature, humidity, wind speed, and so on. And this is collected in real time, and all the data is fed to HSDS. So we've had this running on a test site in University of Virginia for 2 years now, and we're just about to start North Alaska data collections. So it was delayed because of COVID, but finally it's back on track. So it'll be exciting to have that going. And finally, a few references for further reading. Okay, that's the end of my talk. I hope I used the right amount of time. Any questions?
Thanks, John. Let's see if there is question in the chat. In the audience, I don't know if you have questions.
John, quick question about attributes. How are those stored? Are they stored as JSON files or are they binary blobs?
Yeah, so each group is a JSON that has information about all the attributes for that group. And similarly, a dataset JSON has JSON for the dimensions, the type, and so on, and also the attributes. So potentially this would be a problem if you're storing like millions of attributes in one group, because you'd have quite a large JSON file to deal with. I think it would still be workable, but it might be some performance aspect to that. But I haven't come across anyone with that particular issue, so it hasn't been a priority. Do you yourself have to deal with large number of attributes? Curious about how it's stored.
Not a large set of attributes, although I think there's some consideration whether some attributes should be data sets or should they be
yeah,
attributes themselves.
It's kind of a user thing, right? You know, it's two users' perspective. But anyway, there's in Patient's GitHub, we have a formal definition of the data model. If you're curious, you can take a look at that.
Great, thank you.
Hi, John, can you hear me?
Yes.
Okay. No, I just saw that you're talking, you mentioned H5PyD still. Is this still maintained? You know, you still recommend it?
Recommended. I think if you're a Python user, that's probably the easiest way to use HSDS. So the you can always talk REST directly, right? And H5PyD, I guess if there's a problem with it, is that it's based upon a synchronous style API, meaning that when you use H5PyD, or H5Py for that matter, you make a call and you wait for that response, you make another call, and so on. So there's no real support for doing parallelization or asynchronous programming, right? So if you really need that kind of functionality, you might want to use the REST API directly instead.
Can you hear me?
Yes.
John? Oh,
yeah.
Okay. Question regarding you know, scalability, or rather the bandwidth, the through output that you are able to get through this REST API. So is it actually workable to get really big amounts of data that I need to process, or do you need to somehow also make sure that your computation is running somewhere close in the Amazon cloud to the data? Is this doable, or you don't have to?
Yeah, you would definitely be advised to run the server close to the storage, because a lot of requests, if you imagine I have a 2D data set and I'm reading this in one column of the data set, depending upon your chunk layout, that one selection may cross a fair number of chunks, and each of those chunks may have a fair amount of data. So the server has to bundle a lot of data for each of those chunks from the storage system to HSDS, even though the response to the client might be much smaller, right? It might be 5% of the amount of data HSDS had to process to get that response. So in that circumstance, you're much better off running HSDS on server. So in Amazon, running HSDS in the same region as, say, your S3 bucket is stored. Okay, and you had a question about the data bandwidth. I didn't quite get that.
Can you hear me?
Yep.
Okay, so if then I manage to run it really on the same region on AWS, like the computation, so there the bandwidth like between the nodes, is it like workable? Did you measure that?
Yeah. So right. So it kind of depends on your network topology and HSDS. So if you're running HSDS on Docker, obviously you're limited to one client talking to one server, and whatever the network bandwidth is you won't be able to go beyond that, of course. If you have say HSDS on Kubernetes, where you have pods on different servers, now you have this possibility to scale beyond the bandwidth of a single compute node because you have multiple network pipes and multiple pipes from these servers to S3 storage or whatever, right? So that can give you more headroom as far as processing.
Okay, yeah. Thanks.
Right. Yeah, and then also there's recently I created a test case that measures the streaming performance in megabytes per second. So you can run that and get a sense of what your typical performance would be.
A similar question on or a follow-up on this bandwidth and performance. You have shown very nice numbers how you could really speed up the download part when we are reading from a huge data set simply by using more nodes. Have you performed some tests? We're doing the same actually, the opposite direction, basically writing files. So if I want to stream my data, do you have some numbers if I can go to 100 gigabyte per second if I want?
Right. Yeah, I don't think I've gone to 100 gigabytes, but yeah, I do have a test that streams some gigabytes of data to HSDS and then reads that same data back out again. Right. So it's testing both the write and the read performance. Usually I see a little higher read because maybe it's easier to parallelize the reads than the writes, but they're roughly equivalent.
I see. It would be nice actually to see some numbers as well, but okay, thank you.
Right. Yeah, I'm a little hesitant to say anything directly because it depends so much on, you know, what the application is doing and the particular deployment. But I'd be happy to explore your use case and see what we can do as far as getting some metrics around it.
Perfect. Thank you.
Also, I want to mention there's be a hands-on session on Thursday. For anyone who wants to just try setting up HSDS or exploring this kind of question in more detail.